Hello students, and welcome to the third video in our continuing series on solving inequalities of more complicated functions. And very few things are more complicated than a word problem. So let's work on one of those today. It says here, Dixie Packaging Company has a contract with another firm to design boxes with a volume of at least 600 inches cubed. Squares are cut from corners of 20-inch by 25-inch piece of cardboard with the flaps folded up to make an open box. What size squares should be cut from the cardboard? So let me illustrate here. You have a box that is 20 inches wide, 25 inches long. And what you're going to do is it says cut squares are cut from the corners. So you're going to cut some amount here. Okay? And these are all going to be squares. They're congruent. These are all congruent. These are all 90 degrees. And you can cut these. Notice here, if you cut a really big square, you're going to have a very tall box because you're going to fold the flaps up. If you cut a very small square, you're going to have a wide and shallow. Okay, so large cuts lead to thin and high, or thin and tall box. Small cuts lead to wide and shallow. Okay. But what we're interested in here is something that is at least 600 inches cubed, okay, with the volume. So we can think about the box, the volume of the box in this way, that the volume is length times width times height. Okay. Now the length, we'll use this here as the length. And we'll call X the size of the boxes. So all of these sides of these little boxes, these little squares that we're cutting out here, they have a length of X. So X is the length of the cuts that you're making. So then the volume is equal to the length, which is 25, but you're cutting an X from one side and another X from the other side. So it's 25 minus 2X. The width is 20. That's the size of the sheet, but you're cutting out an X here and an X here. So you're losing another 2X from there. And the height of the box, but when you take this flap and you fold it upwards, it's just going to be the same thing as X. And what we want here is it says at least 600 inches cubed. So that means the volume is greater than or equal to 600. So I'm going to make this substitution. 25 minus 2x times 20 minus 2x times x is greater than or equal to 600. And I'm solving for x here. Now, because this side is not equal to 0, we cannot find the zeros as quickly as we normally do. We have to either subtract 600 from both sides, or we have to just graph two separate functions. So I'm going to graph two separate functions here. I'm going to graph this function in y1, and I'm going to graph this function here in y2. So we'll graph, 25 minus 2x times 20 minus 2x times x, that's in y1, and the other one is 600. And we want y1 to be larger than y2. Okay. So, and the window is always a tricky thing, but you got to think about x here is the size of the cuts that you're making. So the biggest cut, the smallest cut that you can make is 0. The biggest cut that you can make is 10, because if x is 10, you've already cut up the entire width of the box here. Okay. So you're not gonna make a cut bigger than 10, and the scale, that's fine. The y min, well, the smallest volume you can have is 0. The biggest volume, well, we're dealing with 600 here. We want it to be at least 600. So I'm gonna go up to 1,000 here. and I'll increment this by 100. and hit graph. So you see that curve right there, it looks parabolic, but it's actually a cubic. And you see that you have 2 points. You have 2 intercepts here, this point here and this point here. And we want the curve to be above that. So I'm going to sketch this graph. And if Mr. Wen or Mr. Stencil is your teacher, you should know at this point you have to sketch the graph. So this is y1. This is y2 right here at 600. And we're looking for the point where y1 is greater than y2. So it's between this point and this point. You can see this is where the curve is above the line. So we're just going to use our intersection feature here. So if you hit second calc, go down to the intersection. First curve, that's fine. Second curve, that's fine. Guess I'm going to move this here cursor closer to the first point so that it knows what to estimate. So that's about 6 or 1.65 or 1.66. So here, x is about 1.66. Y is going to be 600. Repeat the process. First curve, that's fine. Second curve, that's the line. And we're going to go over here. Take a guess. 6.16. So at this point, x is about 6.16. Okay. So our answer is that x can be anywhere between 6.16 and 1.66. So if you make a cut of 1.66, you have a very wide and shallow box that meets the requirement. Or if you make the cut all the way up to 6.66, you have a very high and thin box, but that also meets the requirement. If you make it anything less than this or way too big, then you do not meet the requirements. So this is our final answer. And this word maximum volume here is a little bit misleading. It's really not the maximum, it's some specific number, okay? But you will get problems that will ask you for the maximum volume, in which case you would just find the maximum point. All right, so again, word problems are difficult. You have to work at them. You have to really think through them and ask for help if you can't get it. And you really have to be able to do them on your own at some point, not just take notes or copy off of what your teacher or your classmates are doing. So keep working at it. If you put in the time, put in the real effort to think about it, you will improve. Have a wonderful day.